All right, so now we're going to apply this note that if we have an orthogonal basis, we can come up with the projection by just projecting onto each element of the basis and add it together. And in this example we're looking at, we actually notice that these two vectors form an orthogonal basis for W, which means if we want to do a projection, we can just project onto each one of these separately. All right, so let's project Y onto W. So I'm calling it Y hat, which is the projection onto our subspace W of the vector Y that we were given here. All right, so if you remember previously, first, actually, I'm going to do an intermediate step. We're going to do the projection onto U1 of Y plus the projection onto U2 of Y. All right, so let's find each of these pieces. How do we project onto a single vector? We have a formula for this. We're going to do Y dot product with U1 divided by U1 dot product with itself times U1. So this is a formula from earlier. And then here we need Y dot product with U2 over U2 dot product with itself times U2. I'm just going to do this. Okay, let's actually do these dot products. So if you do Y dot product with U1, you should get a 0 here. And then U1 dot product with itself is 14. And we're multiplying it by U1. And then Y dot product with U2 is 28. U2 dot product with itself is 42. Definitely double check my dot products. And then times U2, 514. All right, so what do we get? Well, this is just going to be 0. So here we just have this left, which is 2/3 times 514, which is the vector 10/3, 2/3, 8/3. This vector is NW, and it's the projection of Y onto our subspace W. All right, so this vector is NW. That is the closest to our original vector Y, which is not NW. All right, so this is actually going to bring us to orthogonal complements. All right, so when we do this, this allows us to write the vector Y as the sum, this should say sum, of Y hat in W and Z in W upside down T. This is the symbol for complement, or orthogonal complement. So this kind of looks like right angles. So this is our orthogonal complement. All right, so what do we mean by this? What is Z? Why is it the in the orthogonal complement? Well, if we go back to our original picture, I'm trying to put all of this together. All right, if we look at the vector Y minus Y hat, that's going to give us our vector z. And so, let me write that down. Z is going to be y minus y hat. And z, as you can see, is not in the subspace W. However, it's orthogonal to W. That's why it's in the orthogonal complement of W. All right, so let's write all this out. So our original vector y from our example was 1, 3, 5. And then our y hat we found to be 10/3, 2/3, 8/3. All right, when we subtract those, we get negative 7/3, 7/3, 7/3. All right, and so my statement said this allows us to write y, so that means our vector y can be written as the sum of y hat, this one, plus something in the complement, which is the z. So that's interesting. The thing we started with, which is not in W at all, can be written as a vector that's in W plus a vector that's in the complement of W. All right, and then another thing to note with things in the complement and what's going on in this whole situation. So note that y hat and z are orthogonal. What about u1 and z? Yeah, they're orthogonal. So are u2 and z. So anything in the orthogonal complement of W is going to be orthogonal to anything in W. All right, so that is going to bring us to our orthogonal decomposition theorem. All right, so this is a name theorem, so we definitely need to know what it says. The orthogonal decomposition theorem. And it basically says what we just did. We're just going to summarize it all in a nice little neat bow. It says, let W be a subspace of Rn. Then each vector y in Rn can be written uniquely in the form. All right, so W is a subspace of Rn. Any vector in Rn, whether it's in W or not, any vector can be written this way. Y equals y hat plus z. Where y hat is in W and z is in W complement. In fact, if we had our orthogonal basis, so if the set U1 to UP is any orthogonal basis of W then we have the following. Y hat is y dot u1 over u1 dot product with itself times u1 plus all the way to y dot up over up dot product with itself times up. Right? The sum of all of those individual projections. And z is going to be y minus y hat. All right, so that's everything we did, and that is the orthogonal decomposition theorem.